In this work, we present multi-agent collaborative manipulation of deformable objects with predictive obstacle avoidance. Imagine the effort of pouring granular materials from a sack into a hopper, placing a sticky composite sheet onto a mandrel without any wrinkles, or constructing a tent using flexible poles. These tasks, all involving the manipulation of deformable objects, can be efficiently managed with the help of multiple robotic arms working collaboratively. Our goal is to enhance human ergonomics and boost efficiency through robotic assistance in handling these challenging tasks. Traditional industrial robots often struggle in these scenarios due to the unpredictable and complex nature of deformable materials. To address this, we introduce a robotic system that consists of a lead robot and assisting robots. The lead robot focuses on precision tasks, while the assistants handle the bulk of the work, dynamically adjusting to the leader's movements. Our research targets the manipulation of a wide array of deformable objects. This includes handling both one-dimensional objects like ropes and two-dimensional materials like fabrics. Each type poses unique challenges, particularly in terms of stiffness variations. In deformable object modeling, existing methods like mass spring systems, position-based dynamics, finite element methods, and the as rigid as possible method have their limitations. For instance, mass spring systems falter with large deformations. Position-based dynamics, while efficient, have faced criticism for lacking physical interpretability, and finite element methods are hindered by computational intensity. However, advancements in position-based dynamics, particularly the improved iteration-dependent stiffness in the extended XPBD version, offer greater suitability for robotic manipulation. These latest developments enhance convergence rate and stability, facilitating effective simulation of diverse deformable objects. Yet modeling alone is insufficient. The integrity and safety of both objects and robotic agents, especially in environments with a high degree of freedom, are paramount. Our work contributes novel solutions in this regard. In our proposed framework, we focus on the real-time control of collaborative transportation of deformable objects. The main task for assistant agents, governed by velocity control, is to minimize positional errors relative to their target. Simultaneously, they must adhere to critical safety constraints. These include maintaining the structural integrity of the objects being carried and preventing collisions with environmental obstacles and other agents. We have developed a quadratic programming-based velocity controller that calculates minimal deviations from the nominal control output. This nominal output is derived from a proportional controller designed to track target positions. Safety measures are assured using control barrier functions. These include constraints for collision avoidance, overstretch prevention, minimum agent spacing, and velocity limits. All of these are introduced as linear constraints in the controller output, which is then translated into velocity commands for the robotic agents. Collision avoidance through linear constraints is made feasible by predicting post-action object states. We achieve this through multiple simultaneous real-time efficient position-based dynamic simulations and minimum distance calculations relative to seen obstacles. This approach offers a versatile solution, applicable to various types and stiffness of deformable objects in both planar and 3D work environments. Our framework is implemented within the robot operating system, comprising primarily PBD simulation, pose perturbation, and velocity controller nodes. While one PBD simulation node represents actual object states, each agent is associated with 3 additional PBD simulation nodes. These nodes, using outputs from pose perturbation and minimum distance calculator nodes, predict post-action object states. The velocity controller node, implementing our QP-based formulation, computes the appropriate agent velocity commands. Our approach is evaluated through various simulation scenarios. Initially, we demonstrated the transportation of a rope-like object with a single assistant agent, incorporating an obstacle in the path. This scenario showcased the system's ability to adapt and respond in real time, ensuring safe maneuvering around the obstacle while maintaining the task's objectives. Further exploring the versatility of our system, we conducted simulations with a stiff rod object. This scenario mimics real-world applications like tent construction, where stiff poles must be maneuvered around obstacles, such as in the ceiling. The system successfully navigated the object, highlighting its potential in applications requiring precise and safe handling of stiff, linear objects. To test multi-agent collaboration, we conducted simulations with two assistant agents carrying a rope-like object. Each agent, governed by its controller, worked in concert with the other, demonstrating effective collaborative manipulation. This was achieved without internal data sharing, relying solely on each agent's individual observations of the simulated environment. In a more complex scenario, we tested the manipulation of a fabric object with 3 assistant agents. This test not only increased the number of agents, but also added complexity by involving a 3D space with a 2D fabric object. The scenario was designed to challenge the system's limits, particularly in maintaining safe distances for overstretching, avoidance, and collision prevention. Despite the intricate nature of the task, our system efficiently navigated the multiple constraints, affirming its capability in more demanding and realistic applications. Moving beyond simulations, our framework was put to the test in a real-world trial. This involved a single assistant agent working with a rope-like object alongside a leader robot operated by a human. The assistant robot autonomously followed the target positions while maintaining safety protocols. This trial demonstrates the practical applicability of our framework in real-life scenarios, ensuring safe and autonomous following behavior in robotic agents. To conclude, our study introduces a versatile framework that integrates advanced position-based dynamics for realistic simulations with control barrier functions for safety. This framework is proven to be real-time capable through various simulation scenarios and a real-world trial. Future work will aim to extend our research to more challenging scenarios, including dynamic obstacles and further real robot demonstrations. We also plan to demonstrate industrial applicability, particularly in robot-assisted composite layout applications.